Nabla, that triangle is called Nabla, and it comes from vector calculus. It takes its name from an ancient harp with a similar shape. Mathematician William Rowan Hamilton introduced it in the 1840s while working on quaternions, and physicist Peter Guthrie Tait later turned it into a standalone operator. Once, it existed. Nabla spread everywhere physics needed to describe how quantities change through space. Maxwell's equations for electricity and magnetism, the Navier-Stokes equations for fluid flow and weather, and the Schrödinger equation in quantum mechanics all lean on this one symbol. What makes it confusing is that the exact same triangle performs three completely different operations depending on what follows it. Alone, applied to a scalar field, it produces a gradient. Dotted with a vector field, it produces divergence. Crossed with a vector field, it produces curl. Squared, it becomes the Laplacian. One symbol, four jobs, and the only way to know which one is happening is the operator sitting directly beside it. Delta. Everyone thinks delta means change. That's only half the story. Delta comes in two forms, both Greek letters that entered calculus in the 17th and 18th centuries. As shorthand for a difference between two values, think of it as the change in balance line on a bank statement. Delta X, meaning how far something moved. But in the 20th century, physicists needed a way to describe something that isn't spread out over time or space, at all a quantity that is zero everywhere, except at a single, infinitely sharp instant. They reused the same lowercase letter for it anyway, calling it the Dirac delta function. So sometimes delta isn't describing change over an interval at all, it's describing a single spike with no width, where delta pairs with epsilon to define an arbitrarily small tolerance in formal proofs. 3 deltas, 1 letter, and the only way to tell them apart is the equation they're sitting in. Epsilon, an element of epsilon, look close enough to be swapped by accident even by trained mathematicians, despite having no real relationship. Augustin Louis Cauchy introduced epsilon in the 19th century when he needed a placeholder for some arbitrarily small positive number while formalizing calculus. Decades later, Giuseppe Pino needed a symbol for belongs to a set and deliberately borrowed epsilon's rounded shape in 1889, stretching it into what we now use for set membership. He didn't want to invent something from nothing. He wanted a symbol that already looked settled and formal. That shared ancestry is exactly why the confusion persists more than a century later. In analysis, is a quantity, usually a small tolerance in a limit proof, in set theory, is a relationship between an object and a group it belongs to. Sigma. Picture a grocery receipt. Every item on the list gets added into one final total at the bottom. That's exactly the job capital sigma does in mathematics. Leonhard Euler popularized it in the 18th century as shorthand for add up everything in this list, with an index below marking where to start and a range above marking where to stop. Lowercase sigma took a completely separate path a century later, when Carl Pearson needed a way to measure how spread out a set of data is around its average, and it became the symbol for standard deviation. Think of, as a measure of how typical is this data point in quality control, engineers aim for 6 sigma precision, meaning only about 4 defects per million, a bar so tight it's become a shorthand for near perfection in manufacturing. So capital always signals an operation sum this up, while lowercase signals a specific real-world quantity. Pi is the ratio between a circle's circumference and its diameter, and it's been approximated since Babylonian and Egyptian times, long before the symbol existed. William Jones first used the Greek letter for it in 1706, and Euler's adoption of it decades later locked it in for good. Here's the part that surprises most people. Mathematicians have calculated pi to trillions of digits, purely as a computing benchmark, but NASA's engineers use only about 15 digits of pi to plot spacecraft trajectories across the solar system. Anything beyond that adds no meaningful precision at distances measured in millions of miles. The real source of confusion isn't pi itself, which never changes meaning, but its capital sibling, which does something entirely different. It multiplies a sequence of terms together, the same way sigma adds one. Because the two look like the same letter at different sizes, it's easy to assume they're related numerically. They aren't. Lowercase pi is a fixed number, capital Pi is an instruction to multiply, and the only thing they share is the alphabet they came from. The integral sign, Gottfried Wilhelm Leibniz, needed a way to represent adding together infinitely many infinitely thin slices of something, the core idea behind integration, so in the 1670s he stretched the letter S from the Latin word summa, meaning sum, into the elongated symbol still used today. It spread through Europe alongside the rest of his calculus notation, and eventually outlasted Isaac Newton's rival system entirely. As the idea grew, so did the notation, double and triple integral signs stacked together for area and volume, and a circled version, specifically for integrating around a closed loop, common in electromagnetism. The confusion rarely comes from the core symbol, which stays consistent. It comes from what surrounds it. A single, with limits a and b sums along one dimension. 2 or 3 stacked signs sum across 2 or 3 dimensions at once. The circle through the sign is a specific flag, meaning the path being summed over loops back on itself, which changes the physical meaning of the entire equation, even though the base symbol never changes shape. Partial derivative looks almost identical to an ordinary d, and that single missing stroke has caused more wrong answers in physics and engineering than almost any other notational slip. Adrien-Marie Legendre introduced the rounded form in the late 18th century, and Carl Gustav Jacob Jacobi standardized it soon after, because multivariable calculus needed a way to say differentiate with respect to this one variable while every other variable stays frozen in place. An ordinary d, as in, assumes f depends on nothing but x. A partial, as in, is a promise that other variables exist and are being deliberately held fixed. Infinity, everyone assumes infinity is simply the biggest thing there is. That's only half the story. There isn't just one infinity. John Wallis introduced the sideways 8 symbol in 1655, and for 2 centuries afterward it just meant unbounded, a quantity that keeps growing forever. Then, in the late 1800s, Georg Cantor proved something that unsettled much of the mathematical world at the time. Infinite sets could be compared, and some infinities are provably larger than others. Here's the part that breaks intuition. There are infinitely many even numbers, and infinitely many natural numbers, and even though every natural number obviously outnumbers the even numbers within any finite range, the 2 infinite sets are exactly the same size, because every natural number can be paired 1-to-1 with an even number. Size, for infinite sets, doesn't work the way it does for finite ones. The plain infinity symbol only ever captures the unbounded limit idea from Wallis's era. The moment mathematicians needed to compare different sizes of infinity to each other, they had to invent an entirely new symbol, because alone was no longer enough. Aleph. That new symbol was aleph, the first letter of the Hebrew alphabet, which Cantor deliberately borrowed in the 1890s specifically, so it wouldn't be confused with any Greek or Latin symbol already used for finite numbers. He labeled the smallest infinite size the size of the natural numbers aleph null, and larger infinite sizes got higher subscripts. The idea was controversial enough that Cantor faced sharp public opposition from established mathematicians of his era, including his former teacher Leopold Kronecker, who rejected the entire premise that infinity could have different sizes at all. What makes aleph genuinely strange is this. Aleph null describes a quantity larger than any finite number you could ever name, and yet aleph 1 describes something still larger than that, an infinity bigger than infinity. Aleph numbers are never interchangeable with the plain infinity symbol, describes an unbounded limit. Aleph describes a fixed specific size of a specific infinite set, and confusing the two is one of the most common mistakes students make moving from calculus into set theory. Big O notation uses a capital letter O, easily mistaken for a 0, to describe how the resource cost of an algorithm grows as its input gets larger. Paul Bachmann introduced it in 1894 to describe growth rates of functions in number theory, and Edmund Landau popularized it shortly after. Computer science adopted it decades later, once algorithm efficiency became a practical problem rather than a purely theoretical one. Here's the part that surprises people. The difference between big O of n and big O of n squared isn't academic. On a modern computer, a poorly chosen big O of n squared sorting algorithm run on a large enough dataset can take longer to finish than the current age of the universe, while a big O of n log n algorithm on the same data finishes in seconds.